Well, how do you all? Thanks so much. This would normally be a Wilbur talk, but he wasn't able to be here, and he had intended to give a talk about some of the Scheme program transformations that we do in a sequence at the IU 311 undergraduate course. But since Will couldn't be here and Dan couldn't be here as their perpetual understudy, I'm going to try and take you on a tour through what it is that we do with students and how we can kind of get them from squinting at denotational semantics in the distance to squinting at operational semantics in the distance over the course of a semester. But of course, we're going to do it in 90 minutes. Normally, this would all be done on a big whiteboard or blackboard if the rooms are actually right and proper, but we're running a little low on that also. So if you want to try and follow along, two things. One, I think you'd have a lot more success looking on the Zoom stream. So if you want to jump on that and turn off your microphones in here, you might have a better chance of being able to see the screen, although I'll try and keep the font as friendly as I can. The other thing is these materials are, everything we need to start with is at that URL. You can download and all the goodies that you need will be there. But after this, I'll go ahead and put them up as, so even if you didn't get to follow all the way along, you'll have a step-by-step sequence through which hopefully you can kind of replay it later. Yes, finally, in the Dan and Will spirit, this is not going to be a slide talk. This is going to be an Emacs talk in which we will either succeed epically or fail epically. So I can't, if you enjoy watching NASCAR in case something goes wrong, then stay tuned. All righty, so the 311 course assumes that students have had a little bit of intro to Scheme, but this very well could be their second programming class in Scheme. They've transitioned to using Racket. Don't let that scare you there. Now it's Scheme. And so we're going to use an S expression-based syntax for the language of our interpreter. This is going to be following one of notion of Donvy, the idea that we can make program transformations, like compiler transformations, the sort of things that we can implement in programs, on programs. And so we'll be, over the course of this, eventually taking a big, fully higher order interpreter, CPSing it, lifting lambdas up, defunctionalizing our environments, closures, continuations, and then changing it all to use entirely global variables, to use labels and go-tos. And once we've got it set up to conditional basic block go-to kind of format, then we're going to use a little tool I've got left over in the back pocket to trivially kick it over to C. And if all goes well, then by the time we're finished, you'll have learned that factorial 5 computes to 120. So, define, eval, expr, env, and we'll use the racket match primitive. If you're into Scheme, then there was Oleg had a nice little matcher that you could implement in one line of code that we've been doing in Scheme, but I think most everybody's schemes nowadays will have some kind of pattern match primitive. The language, as I said, is going to be S expression based, so we can distinguish lambda xb and rator rand for the operator and operand. To keep the names straight, we found that M and N, or E1 and E2, tend to be difficult names for students to remember and pronounce, and so shorthand operator and operand were nice and convenient names. This is a teensy-tiny lambda calculus, but in order to do something exciting, we'll have toss numbers in just so we've got constants that evaluate to each other. And I should have... No, don't ignore. This is, I'm counting on having a room full of you to help spot the bugs in order for this to go through in 90 minutes rather than a semester. Let's see, eval, expr, and I want to do like a real big fancy program, something that will exercise the bejeebus out of this. Lambda x, lambda y, x on 5, and then 6. And we'll run that. That is a mighty beefy program as far as I'm concerned. For the language of this interpreter, it has application, variable lookup, lambda abstraction, and it tests to see that we can look something up pretty deep in the environment. That's a mighty serious program. So we're going to first take in 5, and then take in 6, and we'll return 5 back out of there. So we should be able to get check equal, if you've got this built in. If not, you got something else.
I think we need to pass a hash to eval x.
Yeah, thank you. So normally this would be normally you would imagine having some sort of a nice, pretty data structure environment. And instead, I'm going to do everything in higher order functions entirely with lambdas. Thank you. No, I would have tried to run it. Lambda y, and we'll have a nice, friendly error message. Error. There we go. So if we try and look something up in the empty environment, we should get swatted. I love this little thing. Will likes to call it the Maxwell equations of programming. A small, tiny interpreter that once you understand this, you kind of understand the whole picture. But I found that, unfortunately, folks, if they miss one thing, they can figure it out from the rest, and you can recompute it. But if you get 2 things wrong, or if there's 2 pieces you don't understand, then invariably they interact with one another in a way that you can't recover from a double error. I'm going to try and do this in sort of a smallest fashion that I can. Evaluation, an interpreter, is just another program, and we try and recur structurally. So to evaluate an application, we'll evaluate the operator in the environment. And we'll evaluate the operand. And once we've evaluated both pieces, we will take the result of evaluating the operator, which is going to be a racket function. And you know it's going to be a racket function because we're about to call it like a racket function using racket's application here to whatever value we got back out of the operand. So this tells us that we're using functions, racket functions, to implement our closures. And we're also going to be using racket functions to implement our environment. I used N as the shorthand name for numbers, and Y as the shorthand name for the variables. Anybody know the reason? Yeah. I'm sorry? That's a good, who's on first? The reason is because in the lookup, it spells ENVY, and the imperative programmers are envious of our ability to pass functions as arguments and receive functions as values. So the closure is, we're going to implement these as racket functions, taking in the actual parameter. And once we receive the actual parameter, we'll evaluate the body in an extended environment. So the standard environment you're working with would be plain old ENV. And nothing up our sleeves here, that's a perfectly valid name for an environment. It's only once we've received the actual parameter, as well as the formal and the body we want to evaluate, once we have all the pieces, can we evaluate the body in an extended environment. So if that's a one-argument function that takes a variable and returns a value, then lambda y, env y, should also be a one-argument function that takes a variable and returns a value. Nothing up our sleeve there, but now we've got a name for the input to this environment to talk about. We've got a y is the input, and that means that I can modify the behavior of the old environment. If EQV xy, return A, otherwise we'll look it up in the environment. So this guy here is an environment. It's a mapping from variables to values, and we have here an expression and environment return value. So my environment should take a variable, here represented as a symbol, and return a value. If the thing that we're looking up is exactly the formal parameter here, then we'll return the actual. Otherwise, we'll recur into the environment. So you can think of this as a rather annoying, highly functional way to extend a dictionary. But it sure does look pretty, and this is something I can show my friends. I'm in a department of mathematics and computer science, so I have to be on the lookout. This is the kind of thing I can show my mathematician colleagues, and they'll believe that, yes, this is something meaningful. Okay, cool. So that seemed to run, possibly. The other nice thing about this style is that I can, because we're punning using S expressions between the host language and the language of our interpreter, it's easy enough to be able to pick up this expression and run it in the host language and confirm that, yes, in fact, we do get 5 back out. In a lot of other representations, you would have expected to have tags so that I can syntactically distinguish, I know this one's a number, I know this one's a symbol, I know this is an application. But it happens to work really nicely for students when they have the very host language they're working in is a nice little Rosetta Stone that they can use to confirm whatever program I wrote, is this the right kind of thing that I wanted to get back out? So we have the language of our interpreter, and it's nifty, and we think it's grand. And we could add a whole bunch of other primitive forms to this language. Let's see, pick a couple just to be fun. Times. I've got a syntactic multiplication with 2 sub-expressions. We'll use Racket's multiplication and eval the first one in the environment, evaluate the second one in the environment, and when we get the values back, we're representing those as Racket values, so we can use Racket multiplication and deeply pun on the host language as befits a nice, pretty metacircular interpreter approach. What is kind of unfortunate about this is, so let's see, I'd like to, so let's see, we've got my function and an environment, and we sure enough do get back out that's the closure we were expecting. And you can tell because it says hash procedure, and I'm in a scheme that's lucky enough to give me the line number from where that originated from. And that's as good a clue right now as I can give to users as to what it's going to look like. But students hate this because it doesn't look like something. They can't tell if they've got it right. And they get real excited when I finally show them, hey, I can make it so that this is entirely transparent so that you can completely and totally see what's inside your closures, what your environment looks like at this particular point in time. And they eventually get there and wonder why it is we didn't start there. But that's because character building experiences aren't good to go through, they're good to have gone through. So the way that we normally do that would be to make the interpreter representation independent with respect to environments and closures. So there are some places in here where it's manifestly, completely, undeniably obvious, staring you in the face, where we're using higher order functions to represent environments, and where we're using functions as a representation of closures. So somebody shout out a place where we are using, definitely, undeniably obvious that we're using functions to represent our environments. Line 9. Okay, what else? Where else? Line 14. Okay, where else? Environments or closures? 26. 26 down there if you missed it. I left it sneakily down there, but put it just on the page. Can't forget the empty environment is, in fact, constructing environment. And 13 here, we're also obviously representing using our closures, using racket functions, and 16 as well. So we've got a fair bit of work to do. It just so happens to be nice that you can use regular expressions to any place you were calling your environment, like a function. We can replace a call to environment with a call to this apply env function on the environment. And this is going to be a nice, pretty simple, shallow wrapper. Define apply env, env y, and all that's going to do is a very shallow wrapper over the direct application of the environment to the symbol. But now you can't tell from looking at it. You might suspect it, but you don't know it. We can do a similar thing for applying the closure. Define apply clause, CA, and call the closure on the application. And we've now got hanging out just a couple of lambdas that we've created inside the middle of this inside the middle of this interpreter and its call. So let's pull those out, lift them to lift them globally. Define extend env. And it's real nice about this that I don't have to, if I were in there we go. It took a little minute. Dr. Rackett would have had that immediately. But it's, some of the code is different because this is eLisp. Oh, no, I am. But eventually, I mean, there's, okay, it's the same code. X, A, E, and V. If I wait long enough, my editor will let me know that I've made, that these are exactly the free variables So I close over the free variables of that expression, and at no point do my fingers leave my hand. I can copy the header of that function and paste it back in place. And because I closed over the free variables of an expression that I grabbed out of that context, I can take the header using exactly those variable names and drop it back in that context, and we know it's going to work, and that's super duper nifty. We can do the same for define, make clause, make a closure, and the free variables x, b, e, and v. Just the way to do it is you put the variable, the formal parameter with which you're extending the environment, the body, and then the environment that you shall be extending. And I think finally we've got one last little guy in here. Define empty env. And I'm just kind of following the same pattern, so I was constructing an extended environment, I was constructing a closure, and so I'm constructing an empty environment. And my constructor happens to take no parameters, so grand. You know what I'm going to do? I'm going to take it out of the nice little check behavior, because if it's working, you won't see anything, and I think that's a little disappointing. I think it's better if, when we write the program, we can actually watch it, when we run the program, we can actually watch it spit something out. So, okay, I'm going to perhaps belatedly save this as interp2. So that we've got a contemporaneous copy. All righty, so this is not at all what I had been promising you that we'd get to, because I go once again, okay, we'll use it with the empty environment, but you still get a closure as a closure. What I think is neat about this next little bit is that we have a way to turn the environment and closures from higher order functions into data structures, and we can do it one at a time. And it's not going to be too big of a deal right now, but because there's two kinds of environments, one kind of closure, but when eventually we CPS this program, and we'll take the whole son of a gun, CPS it, once we end up doing that, then you've got continuations galore all over the place, and that's going to, you can make a mistake there, and if you're, the terrible thing about manual whole program transformations is you need to screw up just about once for the whole thing to look undebuggable. The advice we give the students is, if it doesn't work, throw it away and start over. Dan says, I don't debug programs. So they've been recently allowed 5 minutes, but if it doesn't work, then throw it away, roll back to your previous version. If they haven't learned Git before this class, they now have the opportunity to learn it. So, oh. Do what?
So just save a copy of it as version 1, version 2, version 3.
We're currently interp3.rkt. Yeah. So, the step at a time. Match env. This is our matcher, and if it doesn't match any of the preceding clauses, what we'll do is we'll apply the environment like a function. I'm testing those mentally, just going through those clauses one at a time. Nope, nope, none of them. And so when we fall through, we should still get 5 out of that. The idea then, what we're going to end up doing is we're going to turn this higher order function representation of an environment to a first order data structure representation. And I'd like to do it in a way that even I can't get it wrong. The only way that I make typos is if I type keys into my editor. So if I can do this with avoiding needing to type keys in my editor, I've got a pretty good shot at getting it right. So, see? Nope. See? I've got, my environment constructor is going to be just a list with a tag at the front of it. We're going to hold on to the formal parameter, the actual, and the environment, and that will be our extended environment. And it's nice that I can pick up the that representation of environments and the body of the function that we've been using before and drop it back in place, and this should still run even though we've only transformed one of them. We'll do the same thing for the empty environment. And at some point, I should confirm that I need error, not error F, or a tilde somewhere, but it's a pretty good error message. And I'll toss these up to the side because these really are now unimportant data structure constructors. This is the kind of thing that even our friends in the C programming language could deal with. I know now that I'm not going to need to worry with higher order representations of environments, so I can leave that line commented out. And I guess what's neat to see is while doing that process, at no point did we need to change the interpreter after we'd lifted those lambdas out. The interpreter and its call were representation independent with respect to environments. They didn't care what representation of environments we used. We kind of shimmed in an interface and then changed the implementation as a way to leak test our interface. And it's not as exciting to do it because there's only one of them. Match our closure, but similar deal. And so I'm trying to do this in a uniform fashion. I know that Racket and Scheme have plenty of fancier features for doing this, but I want this to be the sort of thing where my students have been told to repeat a nearly automatic process and start wondering, well, shoot, this is annoying. Why don't we just have a program to do this? And then those are the ones I have come work with me when they come back or sell it to the next semester's worth of students. Either one I'm happy with. All right, so we have now an interpreter for which we don't use any higher order functions for environments and closures, and we took what had been a very higher order definition and have now turned it into an extremely first order definition. So we could bracket trace, trace define, and so now we can go ahead and take a look at it actually doing its thing. You can now walk through a very mechanical level. You do see You do see the waiting function calls here. But we'll eventually, you know the order of evaluation now if you weren't already Dr. Rackett. We'll build a closure, we'll figure out the value of 5, then we'll apply it, and then we'll have to evaluate we'll evaluate the body, we'll build a closure, evaluate 6, and work our way through. So this is the sort of thing that students are done with by the second or third or fourth week of class. I find that, well, they've had a lot more time. Plus, they've had to implement it on homework, and I've started making them come in one at a time and explain to me the interpreter, and you can always tell the ones from the look of fear in their face. They think they can hide it, but they can't. You know the ones that need to go back and learn it again. All right, so, shouldn't have done that. Should have saved that earlier. Okay, let's do it again. interp4.rkt #lang Racket, and we'll rewrite a similar interpreter entirely in higher order functions, and then I want to rewrite said interpreter in continuation passing style. Define eval expr env match expr, and colon when number of n will return the number. If it's a symbol, then we'll look it up our environment. If it's a lambda, then we'll wait on the actual parameter. When we finally do get one, we can evaluate the body in that extended environment. If EQV, XY, A, otherwise will recur. Cool. That'll look all right. Blop, blop, blop. And our application, we'll just do the regular old recurring. Eval expr on the rater in the environment, and eval expr on the rand in the environment. Close, 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 close. And once again, let's give it a good beefy test. Eval expr, let's see. Lambda x, lambda, ooh, here's another one. How about, let's do left, left, lambda y, and x, and we'll apply 5, and then we'll apply 6 to that. There's a nice juicy program. If you get this right, then adding the add 1, sub 1, concar coder seems much less exciting. Lambda y. Oh boy, I wonder if, has my Unicode failed me? Or is that my auto-highlighting indenting?
Escape sequence.
Okay.
Double backslashes. You need double R. It wasn't R for me. It's around 2 backslash.
I can't even do a frowny face, so it's, now we're aghast. All right. Okay, we've changed, made important changes in our program so that we're now, even though we're extending the environment, we're extending it internally, we're still getting 6 back out. Grand. All right, 6 is the magic number. hive.rkt. Alrighty, so you can do this in a pretty rigorous mathy way, but I feel like if I'm trying to go through in a way that we do it rigorously in a paper, that's tough for me to get across to a whole classroom full of undergraduates, especially if this is their second or third programming class. We found that teaching continuation passing style is just another style of writing programs is something that's been a little bit more successful. So every lambda gets an additional argument k. Oh, I should say, step 0, change the name. Change the name of your program. I don't know about you, but when I've been working with trying to translate programs by hand into CPS, just to get it into my fingertips, why isn't it calling this, why is that not a tail call? And invariably it's because I used the name of the old function, had the old one calling the new, or the new one calling the old one, and it took me 5 hours to realize I'd made a typo. So step 0 is always change the name. CPS takes an expression, an environment, and some continuation K. K stands for continuation because German, and we'll match the expression. The other thing that's nice about CPSing this particular program, they've gone through and done a decent amount of work to CPSing programs, but something that's really nice about this particular program is that we can treat the matches as simple expressions. Programs in continuation passing style with respect to whatever it is that you, for your architecture, your problem at hand, consider to be simple or consider to be serious. And we can treat those matches as simple expressions. We're treating as serious any function that we write or any function that we receive as an argument. And for simple expressions in tail position, you apply K. If the continuation represents the rest of the work to be done, then when we finally finished our computation, discovered that whatever that big arithmetic operation was actually factually computed to the number n, now we can proceed with the rest of what it is that we wanted to do. Hash colon when, symbol y, inv CPS. This should be, inv CPS, y, and k. And inv CPS. Every function that we take in is serious, including the environment. The environment is of a finite length, but if you treat them uniformly as higher-order functions, then the CPSing operation goes through pretty smoothly, and if you try and do some premature optimizations, you end up a little bit later on needing to patch things back up. Lambda x b. So if we have a lambda, then we're going to apply k to the closure. Lambda ak, eval expr CPS, body to an CPSed environment. Lambda yk, if eqv xy, if the two are the same, then we'll apply k to the value we get. Otherwise, we'll pass it along like we did here. And finally, we can choose the order in which we want to evaluate the operator and operand. I've been kind of bothered this whole time that I thought I was writing an interpreter for my programming language, but I wasn't getting to decide the order of evaluation. I was getting that was coming from my host language. I didn't have any choice in whether the operator or operand was evaluated first. And that was a little annoying to me. So I want to be able to decide that for myself. Eval expr CPS, and let's eval the operator in the CPS environment, and that ought to evaluate to a closure. And as we know, a closure in our world here is a serious operation. Body, environment, and can't forget to actually use said continuation that we spent all that work to pass along. So we've got the closure now. See, we can evaluate the operand in that same environment. And now that we've got that actual parameter, we can pass it to our closure along with the current continuation. And sure, better call it with the, okay. Lambda VV, our initial continuation. If my continuation is a to-do list, then I ought to start off with the empty to-do list, and when I finally achieve the empty to-do list at the end, I'm ready to go. So make sure we're not relying on this at all. Grant. Cool, we can even perp6.rkt. Nifty. All right, so I've got a CPS interpreter here, and one of the neat things that you can do now that you've got an interpreter written in CPS is multiplication. Evaluate the sub-expressions and then use bracket multiplication on the result. If less than, evaluate the sub-expressions, use bracket less than on the result. But if I want to implement something like abort or any other kind of fancy control operations, as you well know, recurring the sub-expressions, and then, well, what do I do with that? If I want to implement, say, abort with the value of some expression, I don't know, I've been doing a lot of operations, I got into a place where I'm doing a bunch of multiplications, and it turns out one of those values was a 0, and I knew darn well that we were never going to get a 0. It's nice that I can now eval expr CPS this expression in the environment, and what continuation what I put there for the job of abort is to stop the computation with the value of this expression, then what I don't want to do is reuse this continuation. That's the worst one to use. So we could toss in an empty continuation, lambda VV, and we should be able to abort with the value. More generally, I want to introduce some kind of control operator to capture the current continuation and put it in the environment. And I also want some way to apply that captured continuation later on. So it turns out you don't need to CPS the interpreter in order to make this work. I'll show you how you could do it without a CPS interpreter, and the way we rely on implement our lambda in terms of brackets lambda, our application in terms of Racket's application, our numbers and their numbers, our times and their times. We can implement our let cc x b, and this is, we're going to capture the current continuation, bind it to the variable x, and evaluate the body in that extended environment. And again, I'm right now assuming we didn't CPS it. Well, I'd need some way to actually factually go get a continuation, and I don't have one floating around. If only, I mean, I guess I'd have to rely on my host language to have some capacity to grab a continuation for me. Let's see. So among the giant sea of control operators, and we'll find out if, oh! This isn't going to load. Anybody know why? The Wi-Fi blocks racketlang.org. I certainly do, but but there's a principle involved here. Presumably because it's not type safe. We'll deal with that. It's. That's without that, I'm going to rely on your knowledge of call CC to. All right. So call CC, or call with current continuation, takes a receiver function whose job is to receive the current continuation, whatever is going to be done at this point from this point in the program, and this call CC is going to pass that value into this receiver, which is a one-argument function. So call CC takes a some program, and let's see, Lambda, and so we'll use K as the variable name, and this program is going to pass in, call CC is going to pass the current continuation here, and we'll find out that, yep, that sure enough is a continuation. And if you want to know something about how continuations are represented, we can now interrogate them. They're not numbers. They're not symbols. It's actually implemented as a procedure. And if you want to see what it looks like when you print it, there you go. Used to be a fun little game we play at IU. What's the smallest program that you can put inside call CC and get something interesting? So I think list was our current winner, but maybe you got something else more exciting. And so for call CC, Lambda, X, body, we can rewrite that as this is equivalent to let CC X B. It's rather than using the call CC operation separately and passing in a single receiver, give me the name of the formal parameter and then the body over which it's bound. So we're going to use Racket to give us an actual factual continuation. And we can eval expr, because we hadn't CPS'd it, body in an extended environment, lambda y, if EQV xy, return k, otherwise env of y. So if you didn't happen to have, if you hadn't CPS'd your program, we weren't completely sunk, we could have gotten this to run. But once again, if I want to understand how these continuation things work, showing you that we can implement in terms of the similar form and racket, I don't feel like I've learned a whole lot. So maybe we want to do this so we can rely on less behavior out of our host language. Let cc x be. If I actually have CPS'd my interpreter, then I really do have a continuation floating around here. So eval expr CPS, and we can evaluate the body in an extended environment, lambda y k hat. Hat is a good name for variables in computer science because when you render it in LaTeX, it gets you that nice little pretty hat over the variable names, and that always looks good in print. So if EQV x, y, well, what I wanted to do, if the thing that I'm looking up is actually factually the formal parameter, then I want to return that saved continuation. Otherwise, I'd like to eval or env CPS with y and k hat. But I didn't just want to return it. I actually, whatever else it was I had waiting to do with that continuation, that's what I wanted to do with it. Yeah?
I always wonder why it's okay to pass a continuation to another continuation. Can you explain that, if you don't mind?
Give it a shot. So, there's the continuation that I've saved in the environment that I'm returning as a value that my program wants to do something with. This is the continuation that I've saved, the one I remembered way back yonder, put in the environment, stuck it in my back pocket so I can hold on to it fresh as it was when I got it. Then there's the continuation that's floating around when I need to go look it up in the environment. I'm in the middle of some computation and I just say, hey, tell me what it was that variable x stood for. Go look it up in the environment, and there was a lot of work being done in there, so I had a whole lot of other stuff to do. And we found out that variable wasn't 5 or 17, it was the continuation. So I found the value, and then I want to do whatever it was I was going to do once I found the value. Maybe it's use that saved continuation. Maybe it's just compute 120. But there's the continuation that as a value that I wanted to look at, and then there's the whatever else I wanted to do next, the behavior that wants to go on in my interpreter. Was that useful? Okay. Right now, we've added capturing continuations in the environment, and it's not been very useful for us. You can extend the environment, and if you like burning De Bruijn indices, or you just like beefing up your environment with continuations at every step, you can do that. But right now, it's not much use because we can't do anything with them. So, in addition to capturing the current continuation, I want to be able to throw. This is, yes, oh, did I?
I just want to confirm I understand correctly. So the semantic let CC is to capture the current continuation, but is X to put in the environment.
Yes, sir.
Then you evaluate E. That's how.
Yep. So let's see, what can we do?
Only have a remark.
Okay.
The evaluator in this new pattern, I think we didn't pass the third argument.
I bet you're right. Holy smokes, that would never have worked. Nice. Sorry, name?
I don't really know. Sorry.
No, what's your name?
What's your
Maciek, gold star for Maciek. All right. Yeah.
So where we're using the fact that for apply environment, it still has the function case. Like instead of like having a list representation, this is still like a rocket function, right?
Yep. Well, I have once again gone back and defaulted to using racket function. If continuations, function. Environments, represented functions. Closure, functions. Name something and we're representing it as a racket function. Sure. So let's see. Throw kexp, vexp, and this is a special tagged form of application, and I can tell you why I'm going to do that, or I can just hold you in suspense and leave you wondering. I'm trying to decide which one I like more. Well, now I'm stuck thinking about it, so I'm just going to leave you on suspense then. All right, so we evaluate both subpieces and then figure out what to do with them. Eval expr CPS, vexp, and CPS, and we'll build a continuation to do the rest of the work, Lambda, and we'll call that value V. So let's see, eval expr CPS kexp and CPS, and we'll build a continuation to do the rest of that work, Lambda K. So notice here, now I am actually factually, locally shadowing that continuation that we'd stored up there. That's important. The shadowing, I always thought that sounded more sinister than it should. The shadowing has made sure that once we've introduced a local name for the continuation that was the value of this K expression, we can no longer use, we will no longer use, because we can't access the continuation that had been the current continuation at this point. We've shadowed it, it's not even locally, it's not even lexically available. So now that I've got this variable K and that value, what I want to do is throw. So this is me installing the value of this kx as the current continuation, and I'm going to invoke it with the value of that expression. So this little continuation here is, now that I've got I know what the value of this expression is. What do I want to do with it? I want to do whatever it is that the continuation that I got from here is going to tell me to do. So somewhere in this kexp, we've got a call to look up in the environment, go back 3, 4, 5 continuations ago, remember the dust it off, and get the value, and now I want to use that one. And this is so close to pretty. There's a beautiful 3-letter English version name for a beautiful little Greek letter that seems like it would be a really nice thing to do here. Somebody shout out Greek letters. You all know them. Lambda. Good guess. Love it. No. Kappa. It's also not a kappa, but that would have been a good one too. Yeah, because that kappa is also how you pronounce continuation. Pi? Hat. Hat. Not a Greek letter, but I love it. So what I was hoping somebody would say is, man, it sure seems like I ought to be able to eta reduce there, but I can't, and it's painfully annoying that I can't. It's so close and yet so gross. So if we reorder these, we do the continuation first, and then grab the value. Now lambda v kv does give me a nice, pretty little eta reduction. One reason for evaluating the procedure, the continuation first, and then the argument, is you end up getting this nice, pretty little eta reduction, because lambda v kv, if this is a one-argument function that looks something up in an environment, then this is a one argument function, well, then this is a one argument function that looks something up in the environment. If this is a continuation that receives a value and throws it to k, then this is a continuation that receives a value and throws it to k. Now, what I think is also neat about this is you may have guessed that at some point we're going to have to defunctionalize all these continuations, holy moly. And this is the point where I used to have have handwritten a keyboard macro in Emacs to show off to the students because they were doing it in VS Code or Dr. Racket or something. And I'd say, oh, well, just like, why don't you pop open your keyboard macro recorder, save the value of the marker in a register, do what you need, jump back to the register, and keep going. And they can't do that, and that feels really good. So we should now, I think, let's do, oh, what the heck, why don't we go do multiplication, throw something in there so we've got some real beefy operations to look at. Comment in E2. Eval, expr, CPS, and E1 in the environment, and we'll build a continuation. Lambda V. Eval, expr, CPS, NE2, in CPS, and that call it lambda W. And then finally, we can apply the continuation to the product of V and W. Do one, do another, and that looks kind of, it's already starting, I think, to, at some point in half my class are imperative programmers, and they have been hating these gosh darn lambdas in parentheses the whole time, and this is where they are beginning to start to feel comfortable. Goodness, yes, all right, do it, give me a name. Do it, give me a name. This is the kind of programming that they seem to like. All right, so let's go try this out. Let CC X, and so, let CC X, and what do we do? Okay, we'll do that, and we'll bind that to times 3 of, and I need a function that's lambda, times 3, throw X, lambda, lambda V, V2, I don't know, 7. So what I'm hoping will happen here is that we'll capture the continuation at this point, and then we'll, and just to be sure, let's do, there we go. So that should possibly do something. Capture the continuation at this point, and we'll start doing a multiplication, but decide that in the middle of it, I actually don't want to do that multiplication, and I will pass the value of this function to that continuation, and that what do we have waiting to do at this point in the program is we're going to apply it to 6 and get 7, and then after that we'll apply that, or we'll multiply that by the 8 and get 54. Wait, no. 7 times 8 is 56? Yes, it is. That's how you know it was right, is because I guessed it. All right. So there's a lot of fancy pants stuff going on there, but this is almost more lambdas than the law allows. And I think I'm not going to take it all the way to C by the end of this, but I'm going to see if I can get it to I can't believe it's not C code, and leave it for you all to kick it over the rest of the way. So maybe we should save this as interp 7. All right, so we've got lambdas abound. Let's say every place that we were invoking the continuation, we'll make that apply k. Every place that we were calling the environment directly, we'll call those, and it's going to rightly complain that we haven't implemented apply env, apply k, apply clause yet, and so we'll have to go jump to that. Luckily, these are all pretty easy to write. Define apply k, v, and we'll apply the continuation to its value. Define apply env, CPS, yk, we'll env CPS, yk. And define apply clause, clause AK. Oh, we called it clause CPS, didn't we? Clause CPS, AK. Cool. So nothing up our sleeves, and that still runs. It's nice that we can do, it's nice to be able to use a regex and afterward the program still runs. All right, so we can start lifting up the environments or closures or continuations. It's useful to start doing them from the inside out. So how about define mult outer k? And once again, I get this lovely, I get my editor to tell me what the free variables are, so I can drop that back in. And I can do the same for the inner. Define mult inner k. Any2, env CPS, and k. And I can finish dropping those in. Let's see. And there's a nice little one to do. So we've got a couple of continuations done. Here's another continuation that we need to pull out. And let's see. Define throw k. And it looks like it takes the exp env CPS, and those are the free variables of that expression, so we can go drop that back in. And we'll need to do the empty k, and we'll need to do a couple more of these things. Yeah, and we'll have to finish doing them all, but let's, so let's see if we can get through this. There's only a couple more to do, and I think we can do this. App outer k, and that's going to take CPS and k. Do the same for the inner one, and let's see if this works. Define app inner k. Rand env CPS, and K. All righty. And, oh, let's see. Yeah, we've got our lovely, lovely little error continuation here. Define empty K that, oh, well, no, that's our empty environment. So that's perfectly fine. What I needed was the empty continuation. Empty empty env and empty K. Define empty K. Cool. So do we now have all of our continuations? Let's see. Oh, don't know if you caught that, but I actually did mess up in the regex in 2 places. That makes perfect sense. There you go. So we've got our, I think that's all the continuations taken care of. We've got some environments and closures to finish off, but empty K. So this is the part where it starts to be where you're very happy you've automated this procedure. I'm going to suggest that for each one of these continuations, do yourself a favor and make V the formal parameter you're using inside the continuation. So C, Shift R, V hat. C, Shift R, K hat. Just universally hat all the variable names so that V is now an available variable name for you in every place. There's 2 reasons for doing this. One of them is so that when I pick up the body, I can drop it right in my apply K, and I know the name V will be bound. It's nice to not have to change any variable names. And there's another little place where you'll be pretty excited. C, Shift R, rand hat. C, Shift R, env, CPS hat. C, Shift R, K hat. C, Shift R, V. You don't actually, it turns out, need to do this for all of them. But as a rigorous procedure for if something's tricky, make it rote. Let's see. We've got like that, C, Shift R, V, VX to. So let's see, we've got our environment, we've got, and we've converted one of those, we've got our closure, and well, these are already right, but I'm just gonna,
Is that a racket mode thing, the rename variable?
yeah. I cannot, the best racket con I ever went to was the one where Steve Chang introduced the racket graph library and Greg Hendershot showed off racket mode. That was life-changing. The Dr. Racket IDE is fantastic, but until it has org mode built in, I'm sadly, I can't completely commit. So do we have all of those now? K. That's far too long without running. I don't know about you all, but I feel really uncomfortable when I haven't run a program and I'm making changes like this for about a minute, minute and a half. I'm the sort of fellow who likes to really make darn sure I've got hold of the next vine before I let go of the one I'm hanging on to. So, we've got And this was born out of hours of frustration getting it wrong. Match K, else KV. All right. And so it'll be nice when we can drop in the list. And turn that into a match clause, and it should still go. We can do that for each one of these. Pick up the formal parameter list, drop that in as an actual factual tagged list with those variables, use that same formal parameter list as the front of a match clause, and now go drop that back into our match expression. And we should be able to do that, let's see, yeah, all the way through. Let's see, and at some point, let's see if we can get all these to go through. Da-da-dum. And yeah, maybe I'm not going to actually finish doing the entire thing through to A9, assignment 9 normal form. But I'll get you far enough that I think you can see the benefit of where this is going to go. Da, da. And I just need to have enough of these so that we can believe it, and some line where I can show you what it's going to do. So let's see. Do I have a good one? Cool. All right. So you can transform these one at a time, and it's nice that you don't need to think about variable names because you've already orchestrated your variable names to line up. You can pick up a program with a free variable in it, drop it into some other context, and have your program actually run. And that's a nifty little thing to be able to do. Yeah, so this'll do. This'll do just fine. So I'm going to imagine that we finish this process on all of the other continuations and the closures and the environments. And so what we'll have is a program that's not using any higher order functions, where every serious call is a tail call, where the only fancy things that we're doing are, recursion, conditional branching, and building data structures. So now that every serious call is a tail call, the only things we have that aren't, the only things that we're doing are what we'd call simple expressions. Let's see. So for instance, this call to eval x per CPS is taking the only things that function calls are doing for us, they're passing parameters and maybe changing the variable names. So this is I think the last little trick that I'll be able to get to show you. Let star, and I'm going to change the locally bind names for these simple expressions and change the name if I'm using a different name. So I'll call K the name for that. I'll let env CPS be the name for that one, and xper be the name for this one. And so I can make my call xper, env CPS, and K. I can make it so that all the calls to my series procedures are using exactly the same variable names that we've been using beforehand. We'll do the same for, and once again, you can, at every step of this, run it, and you can confirm that it will work. This is a local operation that you can do. And so let's do another one just for let star. And we'll, let's say, instead of k hat, we'll call this one k. Instead of, and we'll just call this guy v. And we can now do k and v. Yeah, is there anything, do I have enough to show you something exciting with this? I spoke, didn't nest it? Oh, thank you, yeah. Did that go in there? Nope. Cool, thank you. That, you know, and if I'd run it, we would have noticed that, huh? All right, so the reason for having you rename the variables was twofold. One of them is so that you can get that nice little thing about dropping the expressions in without needing to add local lets. The other is it makes it so that the formal parameters to your functions and the local variables that you introduce in pattern matches are completely disjoint. I also want to go to a place where we don't use any shadowing or, well, I'll show you. So imagine that we've done this procedure all the way through. I've made it so that every call to eval expr CPS uses the same formal parameters. Every call to apply K uses the same formal parameters. Then at that point, I really don't need the formal parameters at all. I should be able to, and this is now a whole program transformation. I should be able to turn each of these into a set bang. Yeah, so if I have defined global variables for each of those formal parameters, define k to who cares, define v to be who cares, and as long as I'm not set banging these variables into existence, you can check, once you've checked locally that your sequencing has been correct, you can turn each of these into a set bang, and you're now programming with global variables, set bang, and goto. And this is the kind of thing that I'd be terrified to program in a previous life, but because we can do it with correctness-preserving program transformations, we can end up doing it in a way that guarantees it'll be correct. And yet I'm labeling and gotoing. So let's see. Another way this was put was through one of the lovely Redditors. We don't have to pass parameters if they're all global. No, but really. And if we, okay, let's do another one. Begin, set bang, set bang. And once you have a program that looks like this, that define may as well be something, may as well be a label. We're matching, figure out what case we want to wiggle down into, set bang, set bang, set bang, and then go to. Now this is the kind of program that I can give my friends who program in C and that they'd understood and feel comfortable using. And once you've got it in a format like this, and I might have alluded to this, at this point in the class, the 20% of the students who have been begging to do assignment and mutation and loops and programs like they know how to, these are starting to do the wave. Everybody else is like, why would you do this to me? I liked my lambdas as they were, but this group starts to like it. And if you program it, so the only 3 variables you're working with are code, an environment, and a continuation, you can start to look at these as transformations between triples. In this state, send it to that state. In this state, send it to that state. And that's the kind of thing where they may not get it right now, but if they end up taking a graduate course, they can maybe a little bit later look back and say, oh, yeah, we actually did this in 311. Anyway, there's the entire course is online for about the past 10 or 15 years. I'm happy to go through the rest of this, and I guarantee, no, I'm not going to put this up, because I'm still making students do this next semester and the semester after. But I do have for you the one that I gave them. An example doing this for Fibonacci. So once you've got that kicked over, let's see, A9.9.rkt. A couple other steps. You add you really and truly do turn them into set bangs. Add a trampoline, so you're looping, going through, and then when the bell dings, you hop it out of the oven and jump back before you ever got into it. The little PC to C file, which I've luckily inherited from Will and Ron Garcia and Oleg and a whole bunch of people who've massaged and mangled it from possibly R4RS scheme, will let me transpile into my Fibonacci C and H, and let's see, GCC, fib.c, dash O, A.out. And oh no, I did something wrong with it in a previous state, or my compiler changed. Drat. All right, so there's something trivial I need to go change. I'll make sure I give you that working. But the 14 warnings are perfect. That's correct. The one error is the problem. For which? Fib C. Oh, is that it? Yeah. Hash include time.h in. Oh, where in the deuce? Oh, no wonder. Yeah. Let's try that again. Cool. /a.out. Oh. Well, Fibonacci of 5 is 5. That's good. All right, that's what I had for y'all.